So now I'll start Bernoulis equation. Bernoulis equation. A differential equation of the form, dy by dx plus py equal to q into y power n is called Bernoulis equation in y. Similarly, we can write Bernoulis equation in x. So what we wrote is a differential equation of the form dy by dx plus py is equal to q into y power n. It is called as Bernoulis equation in y. If you observe, this is similar to a linear differential equation with the extra term y power n. So therefore, this can be made as linear differential equation in y by using some suitable substitution after dividing it with y power n. So divide by y power n. Then we get that as 1 by y power n dy by dx plus p into y by y power n is equal to q. Then we have to take the suitable substitution after the cancellations. So I'll get this as 1 by y power n dy by dx plus p into 1 by y power n minus 1 after this cancellation. This is equal to q. Now I have to use this particular thing as the substitution for reducing this to linear differential equation. So take 1 by y power n minus 1 as t. Then differentiating this, we get that as y power 1 minus n is equal to t. I'll write this by taking this to the numerator. So I'll get that as y power 1 minus n is equal to t. If I differentiate this, then I'll get that as y 1 minus n minus 1. And here 1 minus n into dy is equal to dt. We know that differentiation of x power n is n into x to the power of n minus 1. Right? So here we can write this as y power 1 minus 1. So 1 minus n into y power 1 minus n minus 1. So this will get cancelled. So we get this as y power minus n 1 minus n into dy is equal to dt. Or if we differentiate with respect to x also, we can write it as 1 minus n 1 by y power n dy by dx is equal to dt by dx. If you mention here differentiation with respect to x, so we'll get like this: 1 minus n 1 by y power n dy by dx is equal to dt by dx. Now replace, if we observe in this particular equation, we have 1 by y power n dy by dx plus p into 1 by y power n minus 1 is equal to q. So I'll send this 1 minus n on the other side. So that becomes 1 by y power n dy by dx is equal to 1 by 1 minus n into dt by dx. So I'll write this particular equation as 1 and this as 2. I'll use this 2 in 1 using equation 2 in 1. So we get that as 1 by 1 minus n dt by dx plus p into, we have taken 1 by y power n minus 1 as a t. So we'll take that as p into t is equal to q. Now I'll rearrange this so that I can get a linear differential equation. So dt by dx plus p into t into 1 minus n is equal to q into 1 minus n. If you observe, this is a linear differential equation in t. Once we get a linear differential equation, we know how to write its general solution. Similarly, we can write Bernoulis equation in x. Bernoulis equation in x is dx by dy plus px is equal to q into x power n. So in the same way how we solved the previous one, here also we can solve in the same way and we can get the general solution. In the case of Bernoulis differential equation in X. Now we'll see few problems based on these two. Solve x into dy by dx plus y is equal to x cube y power 6. First, we'll try to make it as a linear differential equation. So for that, we have to divide throughout by x. So we get that as dy by dx plus y by x is equal to x square y power 6. If you observe, this is of the form dy by dx plus py equal to q into y power n. So here the extra term is y power 6. So is a Bernoulis equation in y. Bernoulis equation in y. So to reduce it to linear differential equation in y, first we have to divide it with the extra term. So divide by y power 6. So we will get that as 1 by y power 6 into dy by dx plus 1 by x into y by y power 6 is equal to x square. Then after the cancellations, I'll get this as 1 by y power 5. Just now I told you that for reducing it to linear, we have to use this as a substitution. So take 1 by y power 5 is equal to some t. So that gives y power minus 5 is equal to t. Then I can write it as minus 5 y power minus 6 into dy by dx is equal to dt by dx if I differentiate it with respect to x. Then I can write this as 1 by y power 6 dy by dx is equal to minus 1 by 5 dt by dx. So I'll take this above differential equation as 1 and this substitution as 2. Using 2 in equation 1, then we get that as 1 by y power 6 dy by dx. I can replace it with minus 1 by 5 dt by dx plus 1 by x and 1 by y power 5 that can be taken as t, that is equal to x square. Now this is closer to the linear differential equation in t. So just I have to make a change here that multiplying the complete equation with minus 5. So I get that as dt by dx minus 5 by x into t is equal to minus 5x square. Now it is exactly a linear differential equation in t, where p is equal to minus 5 by x and q is equal to minus 5x square. So to find out the general solution, first we have to find out the integrating factor. Integrating factor is equal to e power integral p dx, because here t is depending on x, so integrating factor will also be with x, e power integral p dx. So e power integral minus 5 by x dx, so which is equal to e power minus 5 integration of 1 by x dx, so which is equal to e power minus 5 log x. And just now I told you that k log x can be written as log x power k. So I can write it as e power log x power minus 5. And we also know that e power log m base e is m. So therefore, we can write this as x power minus 5, or the integrating factor will become 1 by x power 5. So general solution is given by t into integrating factor, because the differential equation what we obtained is in terms of t, right? So solution will also be in terms of t. So t into integrating factor is equal to integration of q into integrating factor dx plus c. T into integrating factor we got that as 1 by x power 5, so which is equal to q is minus 5x square into 1 by x power 5 into dx plus some constant c. On cancellation of these two, I'll get that as t into 1 by x power 5 is equal to minus 5 integration of x power minus 3 into dx plus c. Now what is t? We know that is 1 by y power 5. So we can write it as 1 by y power 5 1 by x power 5 is equal to minus 5. Integration of x power minus 3. X power minus 3 plus 1 minus 3 plus 1 plus c. Then we can write it as 1 by x power 5 y power 5 is equal to minus 5 minus 2. So I'll get that as 5 by 2 and 1 by x square plus some constant c is general solution. Similarly, we look at a few more problems on Bernoulis. Solve dy by dx into x square y cube plus xy is equal to 1. Now if I set this term on the other side, we cannot separate the terms, so therefore we have to take the inverse or the reverse one. So we'll write it as x square y cube plus xy is equal to dx by dy. Instead of sending this here, we have to send this one here. So that becomes x square y cube plus xy is equal to dx by dy. If I rearrange it, I'll get that as dx by dy minus xy is equal to x square y cube. If you observe, this is of the form dx by dy plus px is equal to q into x power n. So it is a Bernoulis equation in x. It is a Bernoulis equation in x. So to reduce it to linear differential equation in x, I have to divide with the extra term, that is x square. I have to divide it with the extra term, that is x square. So I'll get that as 1 by x square dx by dy minus x by x square into y is equal to y cube. Then after the cancellation of these two terms, then I'll get 1 by x. So therefore I'll take minus 1 by x is equal to t. If I differentiate it with respect to x, I'll get that as 1 by x square dx by dy. Sorry. If I differentiate this with respect to y, I'll get this as 1 by x square into dx by dy is equal to dt by dy. So I'll replace this term in the other one. So I'll get that as dt by dy minus 1 by x. I've taken that as t. So I'll write it as plus t into y is equal to y cube is a linear differential equation in t, where p is equal to y and q is y cube. So to find out its general solution, first I need to find out its integrating factor. So integrating factor is equal to e power integral p dy. If you observe from this differential equation, dt by dy, t is depending on y. So the integrating factor will also be in terms of y. So e power integral p dy, which is equal to e power y integral y dy, which is nothing but e power y square by 2. E power integral p dy, which is equal to e power integral y dy. So e power y square by 2. Therefore, general solution is given by t into integrating factor is equal to integral q into integrating factor dy plus some constant c. Then t we have taken that as minus 1 by x. So minus 1 by x into integrating factor e power y square by 2 is equal to integral of q. We got that as y cube into e power y square by 2 into dy plus some constant c. Then I'll rearrange the terms so that I can write the solution easily. So I'll write this as y square into e power y square by 2 into y dy plus some constant c. Then I'll multiply and divide it by 2. So that becomes 2 times of y square by 2 into e power y square by 2 into y dy plus some constant c. Put y square by 2 equal to some p. Then, or I can take y square by 2 equal to p. Then I can write here 2y dy by 2 equal to dp. So y dy becomes dp. Then I can write the above integral as 2 times of integral y square by 2 is taken as p and e power y square by 2 is taken as e power p into dp plus c. Then applying again the Leibniz rule of integration, taking this as u and this as v, just like the previous one. So I get that as 2 into, keeping this term as it is, p, integrating this once, so I'll get e power p minus, differentiating this term, I'll get 1, integrating this term one more time, so I'll get that as e power p. If I differentiate this further, that will give you the answer as 0. So therefore we have to stop the process and we'll take here plus c. So this is equal to 2 e power p into p minus 1 plus some constant c. But what is p we have considered? That is y square by 2. So I'll replace it. So that becomes 2 into e power y square by 2 into y square by 2 minus 1 plus some constant c is the general solution. Similarly, we will see one more problem of Bernoulis. Problem 3. Solve dy by dx minus tan y by 1 plus x is equal to 1 plus x into e power x into secant y. If you observe, this looks like a linear differential equation, but here we have the extra term as secant y. So we have to divide throughout by secant y to reduce it to a linear differential. This is not a linear differential equation. To make it as a linear differential equation, I have to divide with the extra term secant y. Given differential equation is dy by dx minus tan y by 1 plus x is equal to 1 plus x into e power x into secant y. Then divide throughout by the extra term secant y. Divide by secant y. So we'll get that as 1 by secant y into dy by dx minus tan y by secant y into 1 by 1 plus x is equal to 1 plus x into e power x. Now on solving this, we know that 1 by secant y is cos y. So cos y into dy by dx minus tan can be written as sin y by cos y into 1 by cos y into 1 by 1 plus x. So this cos and this cos will get cancelled and we get that as 1 plus x into e power x. Now taking the substitution sin y equal to t. Take sin y is equal to t. Then I'll get, or differentiating this with respect to x, I'll get it as cos y dy by dx is equal to dt by dx. So replacing this in the above, I'll get that as dt by dx minus t into 1 by 1 plus x is equal to 1 plus x into e power x. Now this is of the form dt by dx plus pt equal to q. That is a linear differential equation in t, where p is equal to minus 1 by 1 plus x and q is equal to 1 plus x into e power x. So first, to find out the general solution, I need the integrating factor. So integrating factor is equal to e power integral p dx, so which is equal to e power integral minus 1 by 1 plus x into dx, so which is equal to e power minus 1 by 1 plus x dx, and we know that integration of 1 by 1 plus x is log of 1 plus x, so that becomes e power minus log 1 plus x. Then rewriting this, we get that as e power log 1 plus x whole power minus 1, or I'll get the integrating factor e power log m base e equal to m. So therefore this gives 1 by 1 plus x as the integrating factor. So therefore general solution is given by t into integrating factor is equal to integration of q into integrating factor dx plus some constant c. What is t we have written? That is sin y. So we'll replace it here, sin y into integrating factor. Integrating factor we got that as 1 by 1 plus x, which is equal to integration of q into integrating factor. Q, we have 1 plus x e power x, and the integrating factor is 1 by 1 plus x into dx plus some constant c. Cancelling these two, I'll get implies sin y into 1 plus x is equal to integration of e power x, which is nothing but e power x plus some constant c, which is the general solution of given differential equation.